Hi everyone, I'm Romain Cosson from INRIA in Paris, and this talk is about collective exploration, which is the exploration of unknown environments by multiple mobile agents. So, the main question of this talk will actually be whether maze solving is parallelizable. We will make a rather strong assumption that the maze we want to solve is a tree. That's the name collective tree exploration. Now, maze solving is a problem that dates back to the antiquity. We make these assumptions that the maze is a tree, and we will denote from now on by n the number of nodes, which is also roughly the number of edges, and by d the depth of the tree. If there is one agent that's trying to solve a maze, you probably all know that there is one very simple way to do this, which is to always have this agent touch the wall with their right hand and go forward until it finds the exit. By doing this, the agent effectively implements depth-first search and is guaranteed to finish in 2n moves. Now, if there are two agents in a maze, well, there is a very simple generalization. You have one agent put their right hand on the wall and the other agent put their left hand on the wall. And by doing this, they will effectively each explore half of the maze and meet at some point, and when they meet, well, they can share information and they can both go to the exit. So that takes just n moves each, n time steps. Now, what about more than 3 agents? This is what we are going to be talking about, and as you shall see, it's more tricky than it seems. A little disclaimer before I start, which is in this talk we'll be talking about exploration, which is about going through all edges and going back to the origin. From the point of view of worst case complexity, this is completely equivalent to search, which will be like trying to find the exit of a maze. So from now on, I'll be talking about maze exploration, tree exploration. So this setting is actually precisely the setting that was introduced by Fregnault, Gazieniec, Kowalski, and Pelkz in their 2004 paper, Collective Tree Exploration. They assume that there is an unknown tree, T, with n nodes and depth d, and that there are k agents that move synchronously at each round. So this setup was introduced by the distributed community, so they introduced 2 different communication models. The first is a fully centralized communication model. You can just think that agents also have cell phones, and that at all times they share all the information they have, and that's the model that we will consider. But they also consider the distributed communication model where the agents communicate by reading and writing from whiteboards from memory that is located at all nodes. Now, their main result is that they introduce an algorithm that's extremely simple. It's probably the simplest algorithm you could think about, that they call split, and in which explorers, they just split in teams of same size when they find an intersection. And more importantly, they provide a guarantee for this algorithm of the form that the runtime is less than 2n divided by log k plus d. So it might look a little disappointing here because there's only a logarithmic speedup in the number of agents, but as we shall see, this result was not improved in some sense. So it's hard to, it's a little tricky to do the proof, but a proof of a lower bound actually is actually quite simple. So you can see why there's this log k term. So for this lower bound, I'm just going to take this very simple tree that we call the comb, because it looks a bit like a comb. It has depth d, and it has a number of nodes, n that is roughly d squared, because it's a triangle, obviously. So if you use the algorithm split for one round, well, the 4 agents, they will split into 2 teams. And if you use it for another round, well, the 2 agents on the right, they don't split anymore, but those on the left, they do split again. And if you continue, well, the agents will now continue in distinct branches and reach the bottom of that branch, and eventually they will go back and meet again at some deeper node. So as you can imagine, if there are not 4 but k agents, then log k branches will be explored in one such step. And since the exploration of a branch takes roughly d time steps, so you need d divided by log k such steps because there are d branches, and you you explore log k branches at each step. And since each branch takes roughly time d to explore, this means that you need d squared divided by log k rounds to explore this tree, which is exactly n divided by log k. So this lower bound is actually very general and applies to any greedy algorithm. By greedy, we mean that a robot will never go upwards if there is an unexplored edge below. So really, if we want to beat these kind of lower bounds, we need to go beyond greedy algorithms. So just to make a little more formal the analysis that on the notion of speed up, I will use a notion that comes from the world of online algorithms, which is the competitive ratio. You could consider an offline variant of the problem of collective tree exploration, which is the time needed by the agents to cover all edges and then return to the origin if they had known the tree in advance. So in this case, the agents, they will like kind of partition the edges into k subsets and perform the exploration. And opt is just the size of the biggest partition. So obviously, since one agent has to go to the deepest edge and then back to the top, opt is greater than 2d. But also, since there are 2n edges in total, and there are k agents, obviously opt has to be greater than 2n divided by k. So overall, opt is greater than the average. Now remember that the runtime of splits is big O of n divided by log k plus d. So if you use the information, the derivations that we have above, you obtain that split, the algorithm that I just mentioned, has a competitive ratio of k divided by log k. And this was more precisely the analysis that Fregno and Kowalski, Gadziniak, and Pelk did. Now, any greedy algorithm, as I said a little earlier, will actually achieve a similar ratio. And a lot of work followed on collective tree exploration, but this ratio was not improved, either for the distributed or for the centralized setting. So since it was not improved, someone came out with another type of guarantee, which is the regret. So in 2014, Brass, Mora, Gaspari, and Xiao, they proposed another analysis of splits, in which the runtime is bounded by 2n divided by k. Remember that 2n divided by k is kind of like opt, plus terms that does not depend on n. In this case, it was d to the k. So what's nice about this analysis is that if the tree is very dense, in the sense that depth is quite small, but there's a lot of edges, then this runtime is nearly optimal because 2n divided by k is gonna dominate. This term is gonna dominate the other term. Now last year, with Laurent Massouli and Laurent Vienno, we were able to improve this guarantee with another algorithm to log k times d squared, so to a quadratic dependence on d, and that was precisely for the distributed setting. Now this talk is about the centralized setting, on which we are able to obtain a guarantee in that's linear in d, but obviously the dependency in k is much greater. It's actually k to the log 2k, so it's a little more than any polynomial, but a little less than any exponential. And that's using an algorithm that I'll describe. That's called tree mining game exploration. So the reason why it makes a real difference, the linear in D regret, is that it actually provides a new competitive ratio for collective tree exploration. So this table kind of summarizes the results that were before. So first of all, the result of Fregno was a competitive ratio result. Then came the regret result from Bass, and there was no equivalence between both worlds. I mean, both worlds were not so much talking to each other. Then we improved that to d squared. And in this talk, actually, we propose the first linear in D regret, which leads to an improved competitive ratio for collective tree exploration. I'll explain why in a few minutes. Perhaps one thing to note here is that this term, which is the improvement of the competitive ratio, it's exp of square root log 2 log k. So it's more than any polylog improvement, but it's less than any polynomial improvement. So now I'll try to give some sense of what we actually do, and especially explain what the tree mining game is, which is the main technique of the paper, And the rough idea here is that if you use less agents, you might be more competitive than if you use all agents. And I'll start with that. Meaning that I'll start by explaining why a linear in D regret guarantee entails a new competitive ratio. And the lemma that we are using is actually here on the slides. And it's a very, very simple proof, so I'm just going to do it. If you assume you have an algorithm which runs in 2n divided by k plus g of k divided by k times d, if you have this algorithm, then you might as well use it with less robots than what you have. So you could take a fraction, k prime of the robots, and then discard all other that you tell them just stay where you are, the root, and then the runtime of your algorithm will be of the form 2n divided by k prime plus g of k prime divided by k prime times d. Now, if you choose k prime wisely, especially if you choose it to be g minus 1 of k, then you obtain that the runtime is less than this thing, which is precisely a competitive guarantee of k divided by k prime. So this is how, from a linear in D regret, you obtain an improved competitive ratio for collective tree exploration. So it's quite counterintuitive because we actually use a tiny fractions of the robots to improve the competitive ratio. So the way the proof works is by introducing a problem that's in essence harder than collective tree exploration, which is asynchronous collective tree exploration. So in this problem, the adversary, there is an adversary first, and it controls at all times entirely the robot speeds. So alternatively, you could just say it controls which robots move at each time steps. And the player, it pays the total travel distance by the robots before full exploration. Now, obviously, this asynchronous setting is harder than collective tree exploration, so any result derived for this setting will also apply to the synchronous setting. And the first thing you could notice is that this setting is really harder because split is very bad in this case. So for instance, assume that the adversary allows all 4 robots to move, then they will go back to this configuration, but now assume that the adversary only allows the robots on the right to move. Then they will both go down, and then both go up and join the others. And now they have all only diminished by, they have only explored one branch, and this can go on forever. So all branches can be explored by roughly half of the robots. So it's not competitive anymore. Split is not competitive anymore in this asynchronous generalization. So the reason why it's still a nice object is that it becomes actually equivalent to a game that we call the tree mining game, which is much closer in essence to online algorithms. So we can use the toolbox, the large toolbox of online algorithms to solve this game. So let me explain briefly what the tree mining game is about. So in the tree mining game, you have a tree, okay, with a special set of nodes that we call L, or that we denote L, and that we call the leaves, the active leaves. And at all times, you have a configuration of the miners on the active leaves. Active leaf represents digging positions of miners. And in this example here, you have, for instance, 2 miners on the left active leaf and 1 miner on the right active leaf. Now, there's an adversary in the tree mining game, and at each time step, it chooses 1 leaf, which gets x minus 1 children. Exactly. And that leaf is killed, and the children becomes a new leaf. Then the player gets to observe that choice and relocate the miners in the way it wants before the next round starts. Now, the goal of the player is to have a FKD bounded strategy, which is a way to reach depth D in at most FKD moves. And if you have that, you actually have a FKD regret for collective tree exploration. So that's the reduction in some sense. Just to take an example here, the adversary, let's say, chooses the left branch with 2 miners. So x2 minus 1 is 1. So it has 1 children. And maybe the player relocates both miners of the left branch on this new leaf. So the cost gets plus 2. It turns out that this problem, in the case of k equals 3, is equivalent to a very famous and simple online algorithms problem that's called cow path. So in the cow path problem, you have you imagine that you're a farmer, you're located on you have a field that's actually an infinite line, and you start at position 0, and you want to find a cow, and you don't know where it is. It's at some position x, which is at distance absolute value of x. And the question is, how should you do should you explore and look for this cow if you only see it when you are in front of it? So in the world of online algorithms, we're interested by competitive strategies. So a strategy is C competitive if you are guaranteed to find the cow in at most C times opt moves. And actually there's a very simple competitive strategy, which is the best, which is 9 competitive, and it's a doubling strategy. So it looks like that. And you eventually find the goal, the cow. So the reason I'm talking about this cow path problem is that it's actually exactly equivalent to the tree mining games for k equals 3. So this leads immediately to an exploration algorithm in 2n divided by 3 plus big O of d for k equals 3 robots. The idea here is that it's not a greedy algorithm because with this doubling idea, you know when you should go backtrack. More concretely, imagine you start the tree mining game. So you have the tree mining game, which starts with all miners at the root, and the player chooses that node, and 3 minus 1 is 2, so it creates 2 branches. And arbitrarily, you will send 2 miners to the left branch and 1 miner to the right branch. And now, well, the adversary is always encouraged to choose a branch with 2 miners. The reason for that is that if it chooses the branch with 1 miners, since 1 minus 1 is 0, then this branch is killed forever, and somehow it makes the problem simpler for you. So since you know that about the adversary, what you want to do is alternate and double where the 2 miners will be. And by doing this doubling strategy, you actually are guaranteed to have a linear in D bounded strategy and a linear in D regret for collective tree exploration. So obviously, this is not the end of the story. It's a bit more tricky to derive the strategy for k greater than 4. And the main idea is that we define the strategies recursively, and we have this induction relation of C of k is less than ck minus 1 plus k times ck over 2 plus big O of k. And it turns out that this induction relation leads to C of k is a big O of k to the log k minus 1. So we are very lucky here because it's kind of a sweet spot. First of all, if there was a bigger term in the first term, so if it was like C of k equals 2ck minus 1, then the runtime will be exponential in k. And if you have just a middle term, like C of k equals k ck over 2, then you already have the exact same runtime. So you can't add anything on the right term. You will break everything if you add anything. So this leaves us with a lot of open questions, actually. I think the most important one is probably whether you can do any of this with graphs instead of trees. So I mean by that, a competitive ratio or a regret analysis for graphs. So the tricky part with graphs is that the depth in trees is now the graph diameter. And obviously, with just a few additional edges, you can make the diameter of a graph shrink drastically. So it's hard to guarantee any dependency that depends on D. But it's a nice open problem, and there is absolutely 0 competitive results that's known for graphs, collective graph exploration. Another interesting question, I believe, is whether, so we introduced this notion of asynchronous collective tree exploration, but it's unclear whether there is a competitive gap between synchronous and asynchronous collective tree exploration, whether you can quantitatively prove that there are some things you can do in the synchronous world and not do in the asynchronous world. And similarly, though the problem has been around for quite some time now, in its distributed and centralized variants, no one has ever proved a gap between these two variants either. So it's not known whether there are things you can do in the centralized model that you couldn't do in the distributed model. That's it for me. Thank you very much for your attention.